Our department was established in 1995. We started with about 6 faculty members, and from very beginning that we emphasize both studying fundamental geology and also applied geosciences that are problems of society. Today, so we have 22 faculty members covering a broad range of expertise divided into 4 groups: solid Earth and Earth history, planetary science, applied geoscience, and global change and environmental science.
My current research work focuses on the following 4 frontier issues. First, when and how the plate tectonic began start on our planet. Second, when and how the continent blocks were periodically assembled to form the supercontinent, and later it broke up into the small continental fragments. The third, the Earth's tectonic system was operative before the plate tectonic started on the Earth. And the fourth, how the arcing continental block originate on the Earth.
My main passion is to reveal the principles of how the tectonic forces have shaped our planet and other terrestrial planets over the millions of years. I use the microstructural and the macrostructural analysis and the numerical modeling to study the evolutionary history of the mountain belts. Recently, I have been fascinated by how the Earth's crust deforms and its connection to the deeper processes in the mantle. I also use this knowledge to study economic geology, exploring how geological structures control and modify the local deposit within the mountain belts.
I'm leading my group members to study volcanoes on Earth and other planetary bodies. We're interested in magmatism. In other words, these are processes that govern the transport, storage, and eruption of magmas on Earth, and these are tightly related to volcanic eruptions and the hazards produced by the eruptions.
My expertise is in the study of extraterrestrial materials, so there can be materials that come again from the moon, from other planets. And I also study materials that come from the Earth, primarily looking at the early part of Earth's history. I'm also involved in sample return mission, primarily right now the sample return mission from Phobos. So there will be samples brought back from the biggest moon of Mars, and we will be able to understand if Phobos was a captured asteroid or whether it was formed by a large impact with Mars.
My research focuses on modeling the planetary system and looking at the layer outside the neutral atmosphere. So this is a layer that's populated by charged particles and with lots of energetic electrons and ions. So we use supercomputers, create a virtual environment for the planets, and to understand how these charged particles influences our spacecraft, our satellites, and even manned mission in the future.
My research focuses on lunar science and explorations, especially the landing sites of Chinese lunar exploration program, and I spend lots of time to study the geology of those landing sites and especially characterizing the landing sites to analyze the scientific meanings. At the same time, I also study the samples written by the Chinese lunar exploration program.
In my applied urban geoscience group, I focus on engineering geology and geotechnics. In simple terms, I study how soils and rocks behave, especially when we build things like slopes or tunnels in cities. I use a mix of traditional geology, engineering principles, and new artificial intelligence tools to better understand how the ground might move or change, and to help make construction safer and more efficient.
And when I started my research, actually I only focus on local problems, such as
tidal fluctuation, groundwater, airflow in the unsaturated zone, and how land reclamation will modify groundwater system. And then we realized that all those problems are not simply local, and they are also global problems. Our research is unique because we are the first group of people doing this kind of research. So if you want to study coastal hydrogeology, and our university is really the best place.
We're studying everything from the health of our ecosystems and oceans, extreme weather events like tropical cyclones, to ancient climate patterns preserved in rocks and sediments. Our team uses satellite observations, paleoenvironmental analysis, isotopic methods, and modeling approaches to piece together how the Earth system has and will evolve in the past, present, and future.
We hope that we studying past climate change could provide some insight to our future climate will be, in the hope to get us mankind prepared and also informed for the future climate change. This year is our 30 years anniversary, and our department name just changed from Department of Earth Science to Department of Earth and Planetary Science. So we wish to strengthen all the 4 research areas, particularly in planetary science and also the climate change, so that address the pressing issues from global warming.